Welcome back from the break. Today we're going to talk about, this is CS3510, L08B. The topic of today is an easy problem with DAGs, but we're also going to talk about the Floyd Warshall problem. So again, we're still talking about graph algorithms. We're still talking about shortest path problems. We talked about Bellman-Ford, which solves the shortest path problem in a scenario which is difficult. When there are negative edges, perhaps there are even negative cycles. That's when the shortest path problem is perhaps at its most difficult. When is a graph easy to determine if there's a shortest path in? Certainly there's no negative edge ways. You can do Dijkstra's. What if the graph is even simpler? Can you determine shortest paths in... What is a simple case that it's easy to determine shortest paths that's simpler? Yeah. It's a line. Yeah. Okay. We know the shortest path. There is one path. Yeah.
All edge weights are 1.
BFS. Yeah.
The graph is acyclic.
Acyclic.
Happens to be the same as if it's in a line. There's only one possible path to each point.
We'll solve in that case. And I was also hoping someone would say a tree. There's the shortest path. And if a tree is rooted, in fact, there's a unique path, so there's only one path, so it's the shortest path. So trees are also DAGs. So we're going to consider shortest paths in DAGs. Okay. This is much faster than, of course you can take off-the-shelf Bellman-Ford or Dijkstra's, but if you know that it's a DAG, you can do much better, right? What is some properties you know about DAGs? Name everything we told you about DAGs. Start saying stuff. There's an exam on Wednesday, right? So, what?
Directed acyclic.
Yeah, that's what it stands for. Okay, what else? What can you do to a DAG? Just start naming things, yeah. Yeah, anything else you can do? Not necessarily. What are the connected components of a DAG? Each one. There's no path backwards. There's only paths forward. So the strongly connected components of a DAG are each vertex. There's no cycle. You can top sort it. Can you do anything else? So you top sort it. So consider you have a DAG and we top sort it, right? Something like that, okay? Let's say we're trying to consider shortest paths that begin with S. What can we, just by the properties of top sort, what do we know about a top sort? Only a graph can be top sorted if and only if it's a DAG. If it contains a cycle, some edge is going to go that way. We know a top sort is a representation of the graph. It's not necessarily unique, but all the edges of the DAG go that way, right? That's the way you think about the DAG, the top sort. It's like shoes and socks. It's what order you do things in. You have to do this before you do this. It's the prerequisite and so on, right? So given this, we know that the graph can be top sorted. How can the top sort help us find shortest paths in a DAG? What do we know about, let's suppose we're computing the shortest path of some intermediary node, let's say B. What do we know about the shortest path to B from S? Yes?
Definitely won't go through C or anything to the right of B.
Yeah, exactly. Anything to the right of B has no path to B. By definition. There's a path from B, but not to B. Same thing with A. The only path to A from S is that edge. There is no path that goes through C to A, and so on, by the fact that it's a DAG. So how can this motivate us to find a shortest path algorithm that's in fact very efficient? Yes?
Just go down the list.
And then do what? But yeah.
Find the shortest path for A, and then find the shortest path for B, and then for C.
Yeah. I mean, that's it. So you're going to look at S, and you're going to look at its outgoing edges and do an update. Look at A, look at its outgoing edges and do an update. Look at B, look at its outgoing edges and do an update, and so on. So if I were to write the code of this, what would it look like? A def, single source, shortest path. DAG, G, L, and let's say the start node is S. But it has to be, it's useful only really if it's the source node, right? For all V in V, dist of V is infinity. Dist of S is 0. Top sort, this graph G, for U in V, but in top sort order. So what that means is we're going to go S, A, B, C because that's the order the top sort tells us to. Now that's not the order that's given to us. The DAG could be arranged in any kind of complicated way. We top sort it and then we loop over the vertices in that order. For each of the outgoing edges, so let's say for U comma V in E, and remember when we write the edge like this, it's coming from U going to V. So it's the outgoing of this when we say for U and then for U, V, and E, right? We say, we update according to those edges. So dist V will update to be the min of whatever its current shortest path is, or if this UV edge makes a difference. Right? If we're looking at a vertex U in top sort order, we've already computed shortest paths to everything behind it, right? So if we're currently examining U, we're looking at how U can update everything in front of it. But that means we've already looked at all the shortest paths to U. So in the same way Dijkstra's pop something out the queue, you don't have to look at it anymore. Here, you don't have to look at it anymore because all the paths to U have been examined. So the shortest path to U is already determined, so dist of U will never update. But you can use dist of U to update future things, to find some dist of V, and so on, right? Questions on this algorithm? Runtime. VE? No? Yeah? Why?
Top sort takes V plus E.
Correct.
And the rest takes. Ooh. A takes E.
Yeah. Not much more. It's not much more. V for E, it's fine. Yeah. The edges are going to be, again, the edges, you're going to loop, each edge is going to be looked at once, each vertex is going to be looked at once. It's going to be V plus E, right? It's not the case it's VE because of the nested for loop, but it's the UV in E is not over E, but the outgoing edges of U. So because each vertex may have outgoing edges, each edge is looked at once. So the analysis there is going to not be VE, but V plus E, right? A little contrived kind of thing there. So let's take a look at this DAG and try to update the things. By the way, faster, shorter, Dijkstra's takes, yes, question?
Can't you just start from S?
How do you know what the source is?
Because you were given it as a,
Sure, let's suppose that. How do you know what the, well,
you were given a vertex. And you're never, the past ones are always going to be infinity. There's no way to get back to them.
I don't think the runtime would be efficient. I'm trying to see if, I mean, I think it's correct, but certainly this explanation is clearer, right? So S is connected to something, which is connected to something, which is connected to something. But you don't immediately get the correctness property. I think the correctness property is still there, but it perhaps would be more complex to explain, right? Sometimes it's about, in practice, I'll tell you when you implement a lot of the, almost all the algorithms in this class, the implementation looks different than the way we do them. And that is simply because there are all kinds of little engineering hacks and tricks and speedups. And that definitely would work. You start propagating from S, I'm sure you're going to find your shortest path that way. But when you say top sort, you get to use all the properties of top sort, and that can imply it's correct. And so you get the proof it's correct for free, essentially. So, but I'm sure that would work, right? Faster or slower than Dijkstra's? Yes.
Faster.
Dijkstra's was V plus E log V, right? So this is just V plus E. It's as fast as linear time. Top sort is what really takes the most time. It's the same thing, right? Let's run it quickly on this, this graph. So we're going to look at the vertices in order S, A, B, C. And as we do so, the dist values are going to update. right? So S is going to update. Nothing at the initialization. Things are going to be initialized to S is going to be 0. This is going to be infinity, 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 right? And that's going to be at the start. Then we're going to look at the outgoing edges of S. And we're going to update each of the outgoing edges of S. So S has an outgoing edge to A. S has an outgoing edge to B. S is shortest distance cannot update because nothing comes before it. So we're going to update the shortest distance to A and the shortest distance to B, right? What is 0 plus 2 is less than infinity. So this is going to be 2. 0 plus 7 is less than infinity. So this is going to be 7. And this is not going to be looked at yet. Now we're going to look at the next vertex, which is A. S is not going to change anymore. A is not going to change anymore. Oops. A has 2 outgoing edges, one of value 3 to B, and A's current distance is 2. So is 2 plus 3 less than the current dist of B, which is 7? Yes. So this is going to be 5, which is 2 plus 3. This edge, we're going to look at this one and this one. So 7 updates C if C is greater than 2 plus 7. So 2 plus 7 is 9, which is less than infinity. So this is going to be 9. Okay. Now A is done. Now we're going to look at B. B has 1 outgoing edge of weight 1 to C, right? So S is going to be done, A is going to be done, and B is going to be done. Now C is going to be weight, what is that? 5 plus 1 is 6, which is currently less than 9. So this is going to be 6. And then C, being a sink, has no outgoing edges. So that's just going to be the same. Doesn't really matter, right? That's how you would update it. And you can see as the time progresses how the shortest paths would update according to, and again, I'm using the word update here to mean we take the min of dist V and dist U plus LUV, right? That's what we're calling the update. We're going to repeatedly run through that in such a linear fashion over the edges. Does this graph work if there are negative edge weights? Does this algorithm work if there's negative edge weights? Certainly there's no negative cycle because it's a DAG, so there's no cycle at all. Don't worry about the negative cycle then. Great. Does it work in negative edge weights? The way to determine this is really, does this have the greedy-like property we described? This is actually a tough question, I think.
I think it does work in negative.
It does work with negative edge weights? Why?
Because essentially just comparing the current path you're exploring to the basically the min, making sure that this to whatever node that is already the min from all the past nodes. So you just have to compare it to the current one and the past min.
Yeah, I mean, basically, we still have by top sort that correctness property.
Yeah.
There is no path to B from anything on the right, and all the paths to B must come from edges that are fully on the left, right? So it doesn't really matter if those are negative because we still consider all paths to B. Now, we really can only do that because there's no cycle, right? We get that for free here when we don't necessarily get it for the Bellman-Ford case when there is a cycle. Not only is there no negative cycle to consider, but there's no cycle. So the negative portion is basically handled for us, right? All I'm trying to say is the difference between Bellman-Ford and this graph versus Dijkstra's is this is closer to Dijkstra's than Bellman-Ford is. Another way you can think about it is while Dijkstra's pops things out of a queue, things are exited, right? Here, after you finish looking at shortest paths to S, you don't look at S ever again. After you look at shortest paths to A, you don't look at A ever again. So in some sense, it's exited from the queue because you already know its shortest path, right? Same property when a vertex leaves the queue in Dijkstra's, right? A is done. We know it's found its shortest path. We don't have to find some negative thing that'll come back to there. That only happens when there's a cycle and a negative edge weight. When it's acyclic, we don't have to worry. So negative edge weights work fine. Questions? Kind of a vibes-based thing, but it's a good intuition to build, and it'll help you to discover and determine greedy algorithms, which are simpler in problems that have them or don't have them, right? If you know there's no greedy algorithm for that, you got to try something harder. Okay, let's talk about another problem. We've only talked about the single source shortest path problem so far. What about the all pairs shortest path problem? So single source shortest path is you have a designated start, and you're looking for the single, perhaps not a tree or anything, but you're looking for the shortest path from your source to all possible vertices, you know? All pair shortest path is you're looking to store and output dist ij for shortest path vi to vj for all I comma j, right? So you're looking for not just single source shortest path, but for every possible pair of vertices, the shortest path for every possible pair, okay? What's a naive way to solve all pair shortest paths given something, yeah? Yeah, so naively you could have something like this. Do Dijkstra's, do Dijkstra's, do Dijkstra's, do Dijkstra's, do Dijkstra's. How long does that take? Yeah, it's going to be v times the time of Dijkstra. You run Dijkstra's v times. If E is dense, how long does this take? Almost. Yeah. Okay, not so good, right? Can you do it better? That's basically the point of today. Can you do it better? Can you do it much better? Answer is no, it turns out. We'll talk about the Floyd Warshall algorithm, which solves this in V cubed. Now, it just shaves the log off. Very creative to shave a log off. This is also a problem that has been very well studied, and like we have no promise that Floyd Warshall is optimal. Floyd Warshall will solve all pair shortest paths for us faster than V Dijkstra's, but not by much. And there's like, what's the state of the art on this problem? Can this be done faster than this? And the answer is, I looked it up. This was like a paper from 2014. It's like V cubed and then over some very, very small, I don't want to even talk about the big O, how this works, but it's some very, very small function here. Like some incredibly nuisance of a function that you would always consider a rounding error anyway. And then the constants to implement this are unreasonable. So in some sense, Floyd Warshall is basically good enough, right? The history of Floyd Warshall is also very interesting because he was inspired to find a solution to a practical problem came from a very unpractical place. He was looking at, there's a proof of something involving regular expressions, if you know what those are. And using the proof of regular expressions, he was able to construct an efficient algorithm. But the proof that he was looking at had nothing to do with algorithms at all. It was looking at encodings of paths in state machines. And using that, he was able to translate that into the world of all pair shortest path, and that's basically what we did, right? So let's just kind of describe how the algorithm works. The algorithm works inductively. So what we do is we define dist I, j, k to be the shortest path from vi to vj only using v1 to vk minus 1, right? So first you consider the shortest paths that only use these vertices. Sort of the intuition is that like you don't need to recompute Dijkstra's each time because a lot of that information is repeated, right? It could be the case you have a bidirectional path and the shortest path from A to B is the B to A, so you don't need to run that twice in such a case. But if you have a shortest path, every path along that shortest path is also the shortest path, right? So let's say this is a shortest path. If you know this is the shortest path to here, you also, let's say this is, let's say S, we'll call this, we'll name these 1, 2, 3, 4, and 5. You know something about the relationship between dist 1 and dist 5 and dist 2 and dist 4, right? What do you know about the relationship between these two values? That's true, but about the answer.
Subset of the first. Is like
Yeah, the path, the literal path and not the numerical answer, is a subpath of the longer path. Here's the proof. Assume to the contrary that the shortest path between 2 to 4 was not fully contained in the shortest path from 1 to 5. Then it would exist some path like that, okay? So where that path is shorter than this path. then you could shorten the path from 1 to 5 by going 1 to 2 to the 4 to 5. Contradiction? There's a shorter path. So certainly this isn't very important, and this is basically why every shortest path graph algorithm works, is that information is highly local in the graph. Your neighbors are your neighbor's neighbors, and so on, and that kind of propagates around. And that's what makes all these algorithms work on graphs when they don't work on other settings, on other more crazy objects. That's why graphs are highly studied for us. It's because all these things hold. So we're just going to define, that's kind of the reason it speeds up. We're going to define the recursion inductively, right? So we want dist ij to be a function of dist ij k minus 1s, right? That's how induction works. So we want to somehow compute dist ijk's as a function, some function of I, j, and k minus 1, right? That's how you do the previous induction, right? So in some sense, you're going to add vertex 1, you're going to add vertex 2, you're going to add vertex 3, and that's going to build up your shortest paths, and then you're going to keep track of all that. Right. So let's suppose we have computed certain values already. We've computed all the values for ij that only use up the k minus 1 vertices. So we've all computed dist I, comma j for all ij, and only using the first k minus 1 vertices. We want to compute dist ij using the first k vertices. So we look at this new vertex k, right? So we have a new vertex vk here, right? But we've already computed, let's say, let's call this I, vi, and let's call this vj, right? We've already computed some shortest paths from vi to vj that don't necessarily go through k. So there is currently a shortest path that goes through here. What is this path from vi to vj that doesn't go through vk called? It explicitly does not go through vk. Yeah. But what is that called? In the notation we're using.
Oh, dist ij k minus 1.
Yes.
Sorry.
So we've currently computed that value, and that's something we've stored. And we're going to look at it and update it maybe. So we've looked at dist ij k minus 1, and that's the current shortest path that's known from I to j, vi to vj. That doesn't go through k. Okay? But we want to now look at what k is going to, we look at vertex k, how does it change things? Well, this path is also known. What is that path?
Dist I k minus 1.
Yes. That path has been computed using k minus 1 vertices. The path from I to k has been computed without k. And we know we have an edge here, right? Is that an edge? Suppose it's a path. Sorry. What is that path? This should remind you of the update we did for the shortest path in top sort, the shortest in a DAG, the shortest path with negative weights with Bellman-Ford and Dijkstra's. So define for me what is dist I, j, k equal to.
Min dist I k minus 1.
So it's going to be I, j, k minus 1, or what?
I k minus 1 plus kj k minus 1.
Okay, that's the answer. Now, what order do our loops go in? How do we loop over it? The graph could contain a cycle, maybe even a negative one. Yeah, like all of them. So that's why it runs, it's v cubed. I'm going to rewrite this, but just to show you, for I in 1 to v, for j in 1 to V, for K in 1 to V. Okay? So you do 3 nested for loops, 1 to V, I, J, and K, 1 to V, over and over. That's why it runs in cubic time. You have 3 nested for loops of to V. Sometimes this is also called the V cubed algorithm for that reason, right? It's too hard to say Floyd Warshall. But let's implement it now more seriously. But that's basically all you do, and that's the entire Floyd Warshall algorithm. It's not very smart, but it's like as smart as one could be in such a scenario, right? It's not necessarily, like, we can't expect Dijkstra's level of elegance on every possible problem we solve. We have to be realistic, and the recurrence here is good enough to even beat a naive solution. So we kind of are happy with this. Floyd Warshall takes on input G, L, for I in V, dist I, comma I should be what? Forget the K for a second. I. 0, yeah. We'll let dist ij be the shortest path from I to j. We're going to sort of be implicit upon the k. We're going to do the k, but it's not going to be defined as part of the 3-dimensional array, right? It'll just be k updates to a 2-dimensional array instead of a 3-dimensional array, right? So now let's suppose we haven't begun doing our loop, but we have answers already, kind of. We have shortest paths of length 1, which are our edges. So what we're going to do is just, if we have an edge, I to j, that's already a path from I to j. So we're just going to put that into our data structure. For I in 1 to v, for j in 1 to v, dist ij takes on L of ij if defined, else it's going to take on infinity, right? So if there's, and this is loose and bad pseudocode, but if there's an edge from I to j, vi to vj, just put that as the current dist. We don't know if there's a shorter path yet, but we know there's an edge of length 1. So that's definitely a path. So we just initialize those. Now here's our inductive cases. What we're going to do is for I in range, we'll say 1 to v, for j in 1 to v, we say dist of ij takes on the min of dist of ij or dist of ik, ik plus dist of kj. But where do we update k here? K, it turns out we're going to update externally here for k in range 1 to v. So we run that k times, right? Pretend I shifted that all appropriately. That's all that's all Floyd Warshall is. And again, the main cost here is a 3 nested for loops of v, so this is going to run O of v cubed time, 3d, right? Questions on the correctness, questions on the runtime before we run through an implementation? Yes?
Is assigning all the direct edges of I to j required?
So when you read the graph, it's going to help in this step when you're reading mins of stuff. The edges have to be read somewhere. So just put them in initialized, and then you can repeatedly read here.
Oh, that reads every single edge.
Yeah. Yeah. So here we read the edges by reading the fact that the edges were stored in the array first.
So you don't even refer back to it.
Yeah. By the way, what is this technique called when you write down stuff and then you read it later? This is dynamic programming. Our next unit is going to be on dynamic programming. Floyd Warshall really is a good example of the first dynamic programming thing. Instead of repeatedly having to recompute stuff, just write down small answers to small problems and store those. And then when you need that answer, don't recompute it, just recall it. We'll talk extensively about this technique, but this is really a first dynamic programming problem. More questions on the code? Floyd Warshall. So let's give a graph, and we'll start updating this graph. Just to make things more complex, let's suppose that the graph is undirected. Okay? Now our dist ij matrix is going to look like the following. We're going to update the shortest path from each vertex to each vertex to be 0. Okay? That's our base cases in some sense. And now for each possible edge, we're going to add that weighted edge into the graph. So let's just go through it. A has outgoing edges of A to D is 9, A to B is 5, and A to E is 1. So this is also going to be, because in this special case we're doing undirected graph, right? The outgoing edges of E is going to be 2 to D. So E to D is 2. The outgoing edge C to D is going to be 7. C to D. Okay. The outgoing edge of C to B is going to be 2. So C to B is 2. Yeah. And the rest should be, I think that's it. Double check I'm not making any mistakes. Okay. So that's how the array is initialized, right? Now what we're going to do is k times, we're going to run the update for all ij, right? So the first k, basically, for again, the vertices here are assumed to be initialized v1 to vk. And then we look at prior subsets of those, right? So in fact, we're going to look at the vertices in some alphabetical fixed order, which is A, B, C, D, E. But let's just run through some updates of this graph, right? We're going to look first at all paths that could go through vertex A. So what paths/edges are going to be updated? A has 3 outgoing edges to B, D, and E. So we're going to consider all possible paths that go through A. What pairs should be updated?
Anything that doesn't include A?
Any that does, because we're considering A now. Right? So what paths go through A? A, BD, BE, and DE, right? Now technically you could say, what about CE and so on? But we haven't done the path through B and then C and then so on in this way, right? So we're considering, like, we have no knowledge of the graph, and then we're only considering paths through A, and only considering paths through A and B, only paths through A, B, and C, and so on, right? So paths that only go through A are going to be BD, DE, and BE. So which vertices are going to be, which values are going to be updated here? Let's update BD first, okay? If the path through BD is going to be considered as the min of the current path through BD, which is infinity right now, and we're going to update it to the min of the path from B to A and D to A, which is going to be what? Sorry, B to A and A to D, which should be what? Yeah. And then just by symmetry, this is going to be here. Okay. What about the path D to E? That's 10, but the shortest path D to E is already 2. So, wait, is that right? Yeah, it's already 2, so we don't update that one. What about the shortest path B to E? B to E is currently infinity, so that's going to update to what? Yes. B to E is going to be 6. Okay. Again, we're updating across the diagonal. We update twice because this is an undirected case. Okay. That's everything that went through vertex A. Are we done with that round? Yeah. Let's run another round. Consider all paths that go through A and B combined. Yeah, both A and B. We currently have the shortest paths that go through A, right? Or don't go through A, because the k minus 1 could be 0. If A is V1, k equals 0 would be no paths that go through A, which would just be direct edges. So now we have direct edges and paths that go through A. We want to look at paths that go through A, nothing before A, nothing, A, and B. So we need to update B. So what paths go through B and A? CD, okay. CD is going to be 2 plus 5 plus 7, which is?
It's 2 plus 5 plus 9.
Sorry, 2 plus 5 plus 9, but that's longer than 7, so we don't update that. What else do we update? CE is another one, and CE is going to be 2 plus 5 plus 1, which, what is that, like 8? Which is going to make, yeah, okay, there we go. Okay, now suppose I just repeatedly did that until we got the answer, right? Why am I not going to do it anymore? The fact that the algorithm takes v cubed means it also takes me v cubed to do it on the board, and so on, right? So believe me that I did the rest. Have faith. Does this work on negative edge weights? Why? It looks like Bellman Ford. That's good enough. What if there's a negative cycle? It's definitely not a greedy style algorithm because you have to go back and look at stuff over and over.
You run an extra loop and see if there's a negative cycle.
I claim you don't need to. You can look at the final answer and determine if there's a negative cycle or not. That is a good observation. Auxiliary computing on the structure, on the information you already have, can that tell you if there's a negative cycle? The answer is yes. But I claim you don't even need to do any auxiliary information. You don't need to do auxiliary computing because you already have the answer. Yes?
If any of the entries along the diagonal are less than 0,
Yes. If there's any entry along the diagonal after you run Kij in v cubed times, if any path from a vertex to itself is negative, that path is on a negative cycle. So there's a negative cycle. So you can either say, I'm going to throw out the problem on the negative cycle, you gave me the malformed input, or you can figure out what to do with that yourself. But that's how you can detect the negative cycle. Done. Right? All pair shortest path in v cubed time. Questions? More questions? All pair shortest path? Again, notice that all of these really use the same update mechanism. They just had to do the local properties of the graph. All algorithms use the same stuff, but different ways. Look at it in different ways. Questions? Yeah.
So could you improve this by a constant factor since you only need to calculate one diagonal?
Can you improve this by only in so let's suppose you cut the matrix in half diagonally. That would improve it by a constant factor space-wise, yes. And I'm sure the NumPy libraries or whatever, if you define it in such a way, they don't actually store it as n by n, they'd store it in some lists or something. I'm sure they do that. Absolutely. But also notice, why is this matrix equal to its own transpose? Only because the graph is bidirectional. Every edge is bidirectional. I did that to make it harder for us to compute some paths or have more paths with fewer edges. But suppose that there were one-way edges, then this would not be the case. Dist ij must not necessarily equal dist ji, and so on. Yes. More questions? Conceptual? Good? All right.